So yeah, let's go ahead and look at number 30 and see what it says. So shown is a topographic map of Blue River Pine Provincial Park in British Columbia. Let's zoom in so that everyone can see this as well as possible. Okay. Draw curves of steepest descent from point A descending to Mud Lake and from point B. Okay, it looks like someone might have already tried drawing them there. I should have grabbed a pencil. All right, pencil, awesome. So from point A, we want to draw the line that's going to, in the direction that's going to descend the most quickly. So if you look at A, and so this is where like, you have to be like, okay, this is kind of hard to read. So A is along this level curve, trying to follow it so until I get to a number. Doesn't appear to be next to any number. So, so when you do this, yeah, so it looks like this level curve it's next to is at 2,200 meters. There's not a lot of labeling here, I feel like. There could be more, don't you think? So let's see. So I see that this one here is 1,000. So if I follow this one for a bit, so it looks like this one here is 1,000. And it looks like, I'm guessing the increment is, gosh, you really can't like see that at all. Let me brighten this up a little bit. That doesn't really help, maybe. Let's really zoom in. Okay, there. That's maybe a little more easy to see. So what I'm seeing is this here, this 1,000 level curve takes us over to here. So this level curve is 1,000. And I'm going to guess that each curve is increasing by 200. So this would be 1,200, 1,400, 1,600, 1,800, 2,000, which makes sense because the one after A is 2,000. So our job is to draw curves of steepest descent from point A. So essentially, if you're trying to descend or ascend as quickly as possible, you're trying to cross as many level curves as possible in the shortest distance. So I'm trying to go from here to Mud Lake. I mean, I feel like they've made it kind of obvious for the first one, you're going towards Mud Lake. So we're going to cross, like maybe something kind of like that. I don't feel like it's super clear that that's exactly the right answer, but I feel like going that way, I'm crossing the level curves kind of as quickly as possible. Let's look at question B, or part B. So if we descend from point B, which way do you think we have to go? Up, down, left, or right? I mean, you might say, so right certainly is not an option because right's going to take us up. And also, by the way, for the person on Zoom, here's the attendance form. Feel free to ask questions if you got them. And also up, I mean, up you are going downward. But to me, it looks like we're going to cross curves most quickly if we go kind of this direction. But again, right, I don't think this question is super specific. Are we supposed to go straight or are we supposed to go kind of curvy? It doesn't really say. So that's probably the best intuition I have about that question. But generally, if we're trying to descend as quickly as possible, we're trying to cross level curves that have lower and lower elevations as fast as possible. Right. And really, I should say the more general way of answering that question is you're trying to cross each level curve perpendicularly. Because if you cross it at a 90-degree angle, you're kind of getting across it as fast as possible. So, for example, if I was starting here and trying to go down as fast as possible, I'd be like, okay, cross, 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 cross. They're not perfectly 90 degrees, but they're pretty close. That's the idea if we're trying to either ascend or descend as quickly as possible. Okay. Yeah, good question. So let's move on, ascend, not really. Move on to the next section, which is section 9.6, maximum and minimum values. And along with that, some optimization. The pen would be a good thing to have. So Our drawing skills are not always excellent. So let me just show you these pictures instead. So we're trying to find a local maximum or a local minimum value. Like here we have a local maximum. Here we have a local minimum. Here we actually have what's called a saddle. If we're trying to find any of those things, we need, and you don't need to draw these pictures. We need to find where we have a horizontal tangent plane, meaning the partial derivatives in both the x and the y direction have to be 0. So to have this happen, what we really need is to find a max or a min. What we need is a critical point where both fx equals 0 and fy equals 0. Now, I should also mention, or they could be undefined. You could have a critical point where one or both of the partial derivatives were undefined. That is also a valid thing that happens. There was something else I wanted to say there. Oh, saddle. So just as a saddle is called a saddle because it looks like a saddle, right? Like, have you ever seen a horse and they put a saddle on it? That's what we mean when we say a saddle, one of those. Also, if you've ever been hiking, you've ever hiked up a mountain, sometimes you go like up, 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 and then you can either keep going over or you can turn left or right and go up towards some other peak. That's also called a saddle because it has a saddle shape. I was also thinking about it, your pants are a saddle, right? The crotch goes this way and then that way. So there's lots of saddles in our lives. It's not too hard to visualize one. So I'll point out that this is just saying that to find a critical point, the gradient needs to be 0. Which again, if you think back to what the gradient means, the gradient is just the direction of the gradient is the direction of steepest increase. So if the gradient's 0, we're talking about there being no increase or no decrease. We're talking about a horizontal tangent plane. So let's do some examples. Let's find and classify all relative extrema for the following. xy equals x squared plus y squared minus 2x plus 4y equal to 3. So just a couple language things, right? When we say relative, that's just another word for local. So you can say local extrema or relative extrema. And when we say classify, we're just trying to determine if it's a max, a min, or a saddle. So that's our job. All right, so first, find the critical values. So we're going to take the partial derivatives. The partial with respect to x is 2x minus 2. And we set that equal to 0. And here it's easy to solve. 2x minus 2 equal to 0 gets us x equal to 1. And then we're going to set fy equal to 0. So fy is 2y plus 4. And that gets us y equal to -2. So altogether, this gives us one critical point. That's the point 1, -2. And now we want to answer, does this function have a max, a min, or a saddle at this point? Well, that requires a little more work. So in 17a, you may or may not have learned about the second derivative test, which is the test that says if the second derivative is positive at a critical point, you have a local minima. Let me show you what I mean real quick. We'll come back to this in just a second, promise. So just a quick aside, let's say we had something like f of x equal to x cubed minus 6x squared. Welcome on Zoom, by the way. You're welcome to ask questions if you have them, either by saying words or by writing in the chat. So if this was our function, here's the derivative, 3x squared minus 12x. And if we set it equal to 0, our critical values are x equal to 0 and x equal to 4. Now, one way to tell if you have a max or a min would be to use the first derivative test. Right? You see if it's increasing, decreasing, or decreasing, increasing, and then it's either a max or min. But you can also look at the second derivative. Now, the thing about the second derivative test is it's not always conclusive. If I look at the second derivative, it's going to be 6x minus 12. If I plug in either one of these critical values, look at what happens. F double prime of 0 is going to be 0 minus 12, which is negative 12, which I don't care. It's negative 12. I just care it's negative. So what does this mean? Well, it means that at this critical point from the first derivative, the second derivative is negative. And if the second derivative is negative, that means the concavity is which way? Right? It's concave down, it's open. Yeah. So we're saying at this point, at 0, the function has to be concave down, meaning that at 0 comma whatever, it's actually 0, 0, we have the relative maximum because the function's concave down there, and it was a critical point of the first derivative. In the same sort of way, look at f double prime of 4, that's going to be 24 minus 12, which is positive. So at that point, at 4 comma whatever, we have to have a local minimum because the function's concave up there and it was a critical value of the first derivative. So one way you can tell whether you have a max or a min is by finding your critical points from the first derivative and then plugging them into the second derivative to see if you have a max or a min by checking the concavity. Well, we have a similar, I should say, an analogous test for functions of two variables. It's a little more complicated, but not a lot. So here's the idea. We're going to find this thing that we call capital D. Capital D for it's the determinant of a 2 by 2 matrix, specifically the Hessian matrix of partial derivatives. It's not super important to know that, but here's what it is. It's fxx times fyy minus fxy quantity squared. I'll point out, since you both know, since all of you know how to take the determinant of a 2 by 2 matrix, I'll just point out that this is the determinant of the matrix of second partial derivatives. fxx, fxy, fyx, fyy. This is definitely the determinant of that. It's fxx times fyy minus fxy times fyx. And then you have to remember that fxy is the same as fyx. So you get fxy squared. Not super important. If you forgot this completely, it wouldn't be a big deal. But you do have to remember this. So this thing we're going to calculate here, well, let's actually calculate it. It's going to be, well, let's see, my first derivative, my fx is 2x minus 2. So I'm going to have the fxx is just 2. fyy is also just 2. Very unexciting. And fxy is what? What's the partial of y with respect to fx? It's 0. So this is not very exciting in that we don't actually have to plug in the critical point, right? We just say that this determinant of the Hessian, this d value, is 4. So if d is positive, one of two things happens. It's either a maximum or a minimum. So if this is positive, then you have to check one of the second derivatives. It doesn't matter which one, fxx or fyy. In this case, both of them are also positive. Sorry, f of x is equal to 2, which is greater than 0. Sorry. fyy is also 2, which is greater than 0. So now I'm going to ask you, just like before, if the second derivative is positive, that means the function is concave up, which means we have a max or a min, definitely a minimum. So we have a minimum at the point 1, -2. I should really say we have a local minimum. It is possible. I was just graphing some weird function the other day on GeoGebra to have like a local minimum somewhere, but it not be an absolute minimum and have like other weird stuff going on. It's kind of neat, but also kind of weird. What else to say about this? I think that's all. So let's look at another example. Let's look at this next example. Yeah, so let's look at f of xy equal to 2x squared minus y squared plus 4x plus 6y plus 1. And again, we want to do the same sort of thing. We want to determine where our local maxima, where our local minima, where our saddles, or what do we have if any. I know it's a long way of saying classify the critical points. That's what we're really doing. So first, we're finding the critical points. All right, let's see. So the partial with respect to x is going to be 4x plus 4 equal to 0. We're going to get x equal to -1. The partial with respect to y is -2y plus 6 equal to 0. Looks like we're going to get y equal to +3. So again, we're only getting one critical point. That's fine, but we'll see other problems where we actually get more. And then to classify, again, we have to find this thing D. So D is going to equal, let's see, fxx. I do like to write it out every time, maybe not every time, but at least when I'm first doing it, I like to write it out so I don't make any mistakes. So fxx is going to be 4. Fyy is -2, and once again, fxy is 0. That's -8. So if D is positive, like in the previous example, you either have a max or a min, and you have to check one more thing. If D is negative, it means you have a saddle. Let's just say we have a saddle at -1, 3. And what's happening with the saddle is you've essentially got this thing where you have a maximum in one direction and a minimum in another direction. So in this direction, right, that point there is definitely a maximum in that direction. Whereas in this direction, that point is a minimum, right? It's the bottom of this curve. It's the top of that curve. We could even, right, we have fun tools here. Except I'm opening over here. Oh, and I'm doing, sorry, one thing. Yeah, let me do that. So it's actually like, I do think it's worth your while to actually graph these things sometimes. Oh, this is not the graph, but that's a two-dimensional graph thing. Right? I want a three-dimensional graph thing. Where are my graphs? Graphing. Yeah, this one, cool. So I think there's a link to this graphing utility in Canvas for you all in case you ever want to use it. It is nice to see stuff occasionally. So if we graph this, 2x squared minus y squared, yeah. And then plus 4x plus 6y plus 1. Oh, it looks funky. So if you scroll, you can kind of zoom out a little bit. You zoom out a bit more. There, you can kind of see it. You guys see the saddle there? So there's your saddle. That's the point we found. If we could click on it, it would be the point x is -1, y is 3, and z is whatever. Oh, you know what you can do? You're smart, maybe. I don't know. Sometimes it's good to play around with this thing. I was hoping it would give me the z value there, but I guess I could figure it out. If I plugged in -1 for x and 3 for y, I suppose I could do some quick math and find that f of -1, 3 is equal to, let's see, 2 minus 9 minus 4 plus 18 plus 1. That's going to be -7, -11, +7, +8. Go back to here. Yeah, look, it's right there. You can see it. It's kind of cool. I mean, it's all right. So anyway, it's good to graph things so you can actually be like, oh yeah, the thing we did to show this was a saddle actually is showing it's a saddle. We have a saddle. So cool. So that point on our saddle was the point -1, 3, 8. The important takeaway here, though, is not that graphs are fun. It's that, I mean, graphs are fun. It's always an important takeaway. But that we can find critical maxes or mins or saddles by using this test. And so let me actually write down the thing. It's not written down. Fine. Okay. So to classify extrema of a function of x and y, we first find the critical values by solving where the gradient is equal to 0. Although in practice, we usually think of it as just setting each partial equal to 0. And then the second thing we do is we calculate d. So d being fxx times fyy minus fxy quantity squared. And then 3 possibilities. First possibility, first 2 possibilities actually. So if d is positive, then you have to check one more thing. If either fxx or fyy is negative, then you have a local maximum. If either fxx or fyy is positive, you have a local minimum. I should also point out, and this is important, if d is positive, both fxx and fyy have to have the same sign. There's no way that this quantity is positive without these 2 things matching. Because if these 2 things are opposite signs, then that's negative, and the negative minus something squared is going to be even more negative. So it couldn't be positive if fxx and fyy are different signs, which is good because if you get that d is positive, you only have to check one of them, and whichever one you want is fine. The other option, the sometimes nicer option, in my opinion, is if d is negative, then we have a saddle. Oh, there is one other option, the unfortunate option. If d is equal to 0, the test is inconclusive, which sometimes means we really don't know, and sometimes means we have to kind of think of another way of seeing it. So sometimes this means we don't know, or sometimes it means do more work. Think outside the box. I'm not sure, the spiral. Like this? Don't know. I'm not seeing it. Because eventually, when the spirals I'm thinking about are in chapter 10. Yeah. That's kind of that's a very different topic. But eventually we are going to talk about spirals. After, like literally after your first test, we'll talk about spirals. So this one, what I will say is this one, the level curves, oh, actually not this one, sorry, the one I'm about to show you. So let's look at a really quick example of this last case. So let's say we have this function, f of xy equal to x to the 6th plus y to the 6th. So let's find the partials. Fx is 6x to the 5th. Set that equal to 0. You get x equal to 0. Fy is 6y to the 5th. Set that equal to 0. You get y equal to 0. So our critical points definitely the origin, 0, 0. 0, 0, 0 if you find the z value. But if we find d, look what happens. D is going to be fxx, so 30x to the fourth, times fyy, which is 30y to the fourth, minus fxy, which is 0. And if you wanted to simplify this, you could. 30 times 30 is 900. X to the fourth, y to the fourth. Now, this is actually our first example where we've had x's and y's in the thing we're calculating, in the d. When we calculate this, when we're trying to find d at our critical point, if we plug in 0, 0, we're going to get 0, which is inconclusive. So from this test, we know 0, 0 is the critical point, but at least from this, we can't tell if it's a max or a min. But we can tell if we do a little bit, I don't really know what to say other than a little more exploration. But if we look at this function, f of x, y equals x to the 6th plus y to the 6th. If we plug in 0, 0, it's going to be 0, right? Let me find a little bit. It's definitely clear that f of 0, 0 is equal to 0. Let me ask you both, or you all can Zoom as well. If you plugged in anything else for x and y, would the output be positive or negative? Positive, right? If you plug in anything else for x and y, you're going to get something positive because they're not both going to be 0, and any number to the 6th power is going to be positive, which means that this is a local minima. It's actually an absolute minimum as well because it's the smallest thing total, but it is definitely a minimum because f of 0, 0 equal to 0 is the smallest possible z value. So sometimes just doing some investigation like that will yield the answer. There are sometimes a question or two like this on homework assignments, and you have to be like, okay, how am I going to show this as a max or min without actually being able to use the test that's available to me? Okay, questions about that? It's kind of it's a little bit weird, but it doesn't come up a whole lot, but it can't go up. Let's do, let's do a couple more examples. I've got one, and then this other one he kind of did in class, so I feel like we maybe don't need to do it, but we can if you guys want. I feel like it's worthwhile. Let's look at this example. Let's look at f of xy equal to x cubed minus 12xy plus 8y cubed. This one's definitely a little bit harder to find the critical points. The beginning is the same thing. We're going to find the partial derivatives. See, it's going to be 3x squared minus 12y. And fy is going to be negative 12x plus 24y squared equal to 0. So you'll notice here that neither of these equations leads to a specific value for x or y. So typically when you get something like this, we have to solve one equation for one variable and plug it into the other one. And it is usually good to avoid taking any square roots of any sides, because often that can accidentally exclude an answer that we shouldn't have. So if I was going to do this, I would probably take, I did it differently in my notes, but I think I would actually do it this way. I'm going to solve for x here. So I'm going to say 24y squared equals 12x, just adding 12x to both sides, and then divide by 12. So that x equals 2y squared. And I'm going to plug that in for x over here. So that now 3 times 2y squared squared minus 12y equals 0. All right, I'm going to simplify. Let's see. 2y squared squared is going to be 4y to the 4th minus 12y equal to 0. I should say 3 times 4y to the 4th minus 12y equals 0. And then I'm going to have 12y to the 4th minus 12y equal to 0. What can I factor out? definitely. What else could I factor out? Yeah, the 12 is not so important, but we might as well. The y definitely though. So I'm left with a y cubed minus 1. One thing I really want to emphasize, well, actually, let's solve this and then I'll point it out. So solving this, I either get y equal to 0 or y equal to what? Oops, I wrote it down before I finished asking the question. Or y equal to 1. What I wanted to point out is there is kind of a less good way of doing this. Some people might try solving this by doing 12y to the 4th equal to 12y and then dividing both sides by 12y. The problem with doing that is you get y cubed equal to 1. You're still getting y equal to 1, but you're losing the y equal to 0 solution. So I want to strongly encourage all of you to not divide by your variables if you can avoid it, because it's often going to lead you to losing one or more solutions. It's always, or almost always, a better idea to bring everything to one side and factor as much as possible. So here are our, well, these are the y coordinates of our critical points. So looking back at x equal to 2y squared, if y equals 0, x is going to equal 2 times 0 squared, which is 0. And if y equals 1, x is going to equal 2 times 1 squared, which is 2. So my critical points are x is 0 and y is 0, or x is 2 and y is 1. And now for each of those critical points, we're going to find capital D. So capital D, which is fxx times fyy minus fxy squared, that's going to equal to fxx is going to be 6x, fyy is going to be 48y, and then fxy is negative 12 squared. So I have 6x times 48y minus negative 12 quantity squared. And here's what I would do. I'm going to simplify this a little bit, but I'm actually going to simplify it. I'm going to be lazy about it because I don't really care so much about the values I'm going to get as to whether or not they're positive or negative. So if I can see that something's positive without actually having to calculate it, it's a better use of my time. So here's what I'm going to simplify this. I'm going to write it as 6 times 48, whatever that is, times xy minus 144. Because I think I don't actually need to know what 6 times 48 is to figure this out. So if I plug in 0, 0, what do I get? Negative number, specifically negative 144, because we can see that it's 0 minus 144. But yeah, you're right. You did the better thing and didn't do all the work. Said, oh, it's negative. Done. That means we have what? We have a max, a min, or a saddle at 0, 0. We have a saddle. Whenever D is negative, we get a saddle. All right, let's look at the other value. We plug in 2, 1. We're going to get 6 times 48 times 2 times 1, but I don't think we need to write times 1, minus 144. And I'm pretty sure that 6 times 48 is bigger than 144. So 6 times 48 times 2 definitely is. So I'm pretty darn sure that that's positive. You could actually calculate it. 6 times 48 is 288 times 2 is big enough to be positive when you subtract 144. So if it's positive, that means we have to do a little more work. We have to look at the second part, one of the second partial. So if we look at fxx, well, fxx, which I didn't write down, but fxx is 6x. And if we plug in the 0.21, that's definitely going to be 6 times 2, which is 12, which is positive, which means we're concave up, which means we have a minimum. So we have a minimum at this point, 2, 1. And I really should say it's a relative or local minimum. perfect question for where it's about to go. So for these kinds of functions, we can't really do that. Like, so typically when we're asked to find absolute extrema, we have to limit ourselves to a region of the XY plane to look over. So for example, let's look at the next example. So actually, yeah, we have time. So I will kind of say finding absolute extrema is very similar to how we did it back in 17a, meaning, again, so if we look back at this example of f of x equal to x cubed minus 6x squared, if I wanted to find the absolute max or min of this function on the interval from 1 to 7, I would do the following. I would first find the critical values. So first derivative equal to 0. And we did this one before. The critical values were 0 and 4. And the second thing to do is to take your critical values and your endpoints and plug them back into the original function. So I'm going to simplify the original function a little bit. I'm going to make it x squared times x minus 6. And then I'm going to plug in the endpoints, x equal to 1, x equal to 7, and the critical values, x equal to 4 and not x equal to 0, because x equal to 0 isn't in the interval that we're being asked about. So if your point isn't in the interval that we care about, it's out of bounds. We don't care about it. Well, let me find the values, and then we'll see what's going on graphically. So I plug in x equal to 1, f of 1 is going to be 1 times 1 minus 6, which is negative 5. I plug in 7, f of 7 is 49 times 1, and f of 4 is going to be 16 times negative 2. Graphically, here's what we've got. So I know that we would have the point 0, 0, even though we don't care about it. And it looks kind of like this. So here's the point 4 comma negative 32. Here's the point 1 comma negative 5. And here's the point 7 comma 49. So we look just from here to here. Oh, well, there's the absolute maximum value. That is the biggest y value the function attains on that interval. And there is the absolute minimum value. That is the smallest value the function attains on the interval. And we didn't even think about this point here, even though it's a local maximum, because 0 wasn't in the interval that we were being asked about. So that's the general idea, is we're going to take our interval, find all the critical values on that interval, and then plug them back into the original function to see if they're maxes or mins. We don't do anything with this D thing that's not even in play when we talk about absolute maximum or minimum. The only difference is now instead of being on an interval, we're going to be on a region in two-dimensional space. So let's look at an example. In fact, this picture that Grant, I wish I could draw as well as Grant. Grant draws really nicely. So here's a picture. We're going to look at, in fact, yeah, we can look at the whole thing. We're going to write this down in a minute. So we're going to find the absolute maximum minimum values on a closed boundary. This is the function we're going to look at first, the function x squared plus y squared plus x squared y plus 4 on the region, all points x, y, where x is less than, absolute value of x less than 1 is less than or equal to 1, and then absolute value of y is less than or equal to 1. In other words, we're looking at all the points in this square, where x is between -1 and 1, and y is between -1 and 1. And I think the words Grant uses are really nice. I'm just going to read them to you. Imagine a room where D is the 4. D for domain. So maybe D is not a great letter to use here since we were just using capital D for something else. So I'm going to call it R just for the sake of differentiating. R for the region that we're looking at. So the region we're looking at is the 4. And the function f of xy is the ceiling. It's the top. X equals plus or minus 1, y equals plus or minus 1 are the walls of your room. So here's a good picture, right? Here's the floor. And there are the walls. Y equals 1, x equals 1, y equals -1, x equals -1. And the question we're trying to answer is, where could the highest and lowest points of the ceiling occur? Well, they might occur in the middle somewhere. Maybe you have a roof that looks vaguely normal-ish. I don't know. Is that normal? Maybe. Maybe in Europe. I have no idea. So one, the maximum or minimum, the absolute maximum or absolute minimum, could occur somewhere in the middle, like this. In this case, the maximum or minimum point will be a critical point where the derivative, the partial derivatives will be 0, or where the tangent plane is horizontal. But you might have a maximum or minimum or a highest or lowest point at one of the corners, like this. Or, and yeah, there's one more picture. So it could occur at one of the corners, like that. Lastly, you ready? You guys ready? The maximum or minimum could occur midway through one of the walls. It could occur along a point along one of the walls in the middle, like this, where it's kind of going up like that. That's also a absolute maximum. So when we do this kind of process, there are 3 things to check. We have to look at critical points. We have to look at corners, and we have to look at critical points along each of the walls. That's the whole idea. So it's a little involved. So let's go ahead and do this. So what we're going to do for f of x, y equal to, and I forgot what the function was already because I'm trying to remember things. X squared plus y squared plus x squared y plus 4 on the region, the set of all points x, y, such that x is between -1 and 1, and y is between -1 and 1. And I do think it's a good idea to draw your region. Specifically because it's good to know what your boundaries are. So I definitely know without a doubt that I'm going to be checking the points 1, 1, 1, -1, -1, -1, and -1, 1. I'm going to have to plug each of those points into the function. And then I'm also going to have to look at the walls, x equal to 1, x equal to -1, y equal to 1. Before I do either of those things, I'm actually going to first find the critical points. So critical points, I'm going to find my partials. Fx is 2x plus y. Set that equal to 0. That's going to give me y equals -2x. And fy is 2y plus x squared equal to 0. Feels a little messy, I got to say. But if I take that and I plug in y equal to -2x there, I get 2 times -2x plus x squared equal to 0. So -4x plus x squared equal to 0. So that's going to give me x times -4 plus x equal to 0. So it looks like I'm getting x equal to 0 or x equal to 4. I feel like I should double check that because this feels, yeah, I feel like I definitely made a mistake there. What did I do wrong? Oh, wow, I really did make a big mistake. And sorry, I was going kind of fast, so you probably didn't have a chance to catch me on it. What mistake did I make? Yeah, exactly. So when I took the partial here with respect to x, I should have had 2x plus 2xy. So let's just do it again. So our fx should actually be 2x plus 0 plus 2xy. That's going to be a little easier to solve, right? I'm going to have 2x times 1 plus y equal to 0. So I'm going to get x equal to 0 or y equal to -1. Now I need to be extra super clear here. 0, -1 is not a critical point, at least not because of this, right? We're saying x could be 0 or y could be -1, but that doesn't mean they both need to be, because what we also need to be true is we also need the partial with respect to y to be 0. And doing this the right way, that's going to be 2y plus x squared equal to 0. So let's plug in our critical points and see what we get. Or I should say, let's plug in our x values. So if x is 0, well, then I'm going to get 2y plus 0 equal to 0. So I'm going to get y equal to 0. So 0, 0 is a critical point. And then if I plug in y equal to -1, I'm going to get -2 plus x squared equal to 0, which is going to give me x squared equal to +2, which is going to give me x equal to plus or minus the square root of 2. Now, this will give me the points -1 root 2 and -1 negative root 2. Again, I want to emphasize here two things. Thing one, 0, -1 is not a critical point. So one more time. Oh, you're right. You're right. Sorry. Thank you. Yeah. I don't intend to make mistakes, but sometimes they do happen. And thank you for catching me on them. So thing one, 0, -1, not a critical point. Thing two, these two critical points are critical points, but they're not in the region. These are not in the region are because the square root of 2 is bigger than 1, or the negative square root of 2 is less than -1. Right? Those points, square root of 2, -1, that would be like over here, outside of the region, or over here, outside of the region. We don't want those. So it's really good to not, right? You don't want to do more work than you need to do. So those points we don't need to check. Now, we're almost out of time and I don't want to keep you late. So let me just talk about the next part really quick. So the next thing we have to do is we have to find the critical points along the walls. So we take our function, x squared plus y squared plus x squared y plus 4, and we actually set x equal to 1. So if x equals 1, here's what we have. We have f of 1 comma y equal to 1 plus y squared plus y plus 4. And we take the partial derivative with respect to that. With respect to y, because there's no point in taking it with respect to x, because we know the partial with respect to x would be 0. So if we do that, we get 2y plus 1. Oh, sorry, thank you. No. And then we set that equal to 0, we get y equal to -1/2. So along that wall, 0, -1/2 is a critical point. It's a pseudo critical point is what I like to call it. So we have a critical point over here at 0, -1/2. Sorry, not 0, -1/2. X wasn't 0, x was 1. So over here, there's another point we're going to have to check. So since we're out of time, we'll leave this till next time. But what I will say is the idea here is after we find all these critical points, we plug them all into the original function and we just ask which one's the biggest, which one's the smallest, and then the biggest one, that's where our absolute maximum is, the smallest value, that's where our absolute minimum is. Sorry, we couldn't get to finishing, but I don't want to keep you too long. So one more time. Right. So then so then we would also, so I'll stick around for a few minutes and actually finish doing this on camera. You're welcome to go. You should go, but I'll finish this on camera. And so then if you want to watch it later, you can. But I'll finish. So for those of you on Zoom, oh, you guys are left. So feel free to go. I'm going to keep talking to an empty room for a minute so you can see it later. So we'd plug in x equal to -1. We do f of -1y is going to be 1 plus y squared plus y plus 4. The partial derivative would be 2y plus 1, set that equal to 0. We get y equal to -1/2. So we also have the point -1, -1/2. But and then talking to no one, we would also do the same for y, for the y walls. So we plug in y equal to 1. We're going to get f of x comma 1 is x squared plus 1 plus x squared plus 4. Taking the partial of that, we get 2x, or really I should have put those together. We get 2x plus 2x, which is 4x, and we set that equal to 0, and we get x equal to 0. So 0, 1 is a critical point on a wall. And then finally, y equal to -1. So we have f of x comma -1 is going to be x squared plus 1 minus x squared, because we're plugging in y equal to -1. So we get x squared plus 1 minus x squared plus 4. And that's just equal to 5. And so there is actually no critical point along this wall because your partial derivative is just always 0. So, right, essentially along that wall, all of the heights are the same, right? If x, so if you think about the function, right, if you plug in -1, the height's always 5. I should be plugging -1 for y. So along this wall, the height, along this wall, the height of the function is always 5. So let me plot our other two critical points here. We had +1, -1/2. We have -1, -1/2. And then we have 0, 1. And then we also have the critical point, of course, 0, 0. Okay, so there's our map of all our critical points. And then what we do is we take all those critical points and we plug them back into the original function. So our function, f of xy, is x squared plus y squared plus x squared y plus 4. And then we're just going to plug in each of them. So we're going to do f of 0, 0. We're going to do f of 1, 1, f of 1, -1, f of -1, -1, f of -1, 1. And then we're going to do f of 0, 1, f of 1, -1/2, f of -1, -1/2. All right, so 0, 0, we're going to get 0 plus 0 plus 0 plus 4. 1, 1, we're going to get 1 plus 1 plus 1 plus 4. 1, -1, we have to be a little more careful here. We're going to get 1 plus 1 minus 1 plus 4. That's going to be 5. In fact, we already know that whenever y is -1, it should be 5 because that's what we saw when we plugged in -1. So this one should also be 5 right off the bat, right? 1 plus 1 minus 1 plus 4. Yep. And then -1, 1, we're going to get 1 plus 1 plus 1 plus 4. 0, 1, we're going to get 0 plus 1 plus 0 plus 4. And then these ones we have to do a little more thinking when we plug them in. So we're going to get, let's see, f of 1, -1/2 is going to be 1 plus 1/4. 1 times -1/2 is -1/2 plus 4. That's going to be 1.25 plus 75 would be 4.75. And I think we get the same thing here, but let's check. We're going to get 1 plus 1/4 minus 1/2 plus 4, which is 4.75. So to answer the question, we have an absolute minimum at x, y equal to 0, 0 with a value of f of 0, 0 equal to 4. We have absolute maxima, and I am using the plural there, at 1, 1 and -1, 1 with value of f of 1, 1 is equal to f of negative 1, 1 is equal to 7. So we have an absolute minimum at 0, 0, value is 4, absolute maxima at 1, 1, and negative 1, 1 with values of 7. You can have more than one absolute max and absolute min if there are more than one place where the highest value is the same. All right, that's all I got. I will see you all on Wednesday.